Thank you very much. So in this talk I will tell you about a theory of quantum gravity, which I claim to be the theory, from a new idea that's called fakeon, which is a new quantization prescription for a particle which becomes a fake particle, which I claim has been overlooked throughout the history of quantum field theory. So the reason why I will claim that this is the right theory is encoded into this picture that many of you will recognize. I will explain to you the reason why this has to do with my claim at the very end. For the moment, some of you already know what this is. Some others maybe don't. So the story is about a new quantization prescription, as I said.
Same as this morning. If I catch something, I close si vede bene tutto? But if I catch that, it's a bit better.
So the story is about a new quantization prescription, as I said, which gives birth to a notion of fake particle. And this leads to a new type of quantum field theory, if you want, which will be a quantum field theory of particles and fakeons. And in particular, in the case of gravity, it allows us to solve the problem of making the theory unitary and renormalizable at the same time. Then we will see some physical implications and predictions. In particular, we will see some predictions that survive the classical limit. The classical limit will bear new features in itself. And we'll see some examples with applications to cosmology. So what is the problem of quantum gravity? The problem is to make it renormalizable and unitary at the same time. Because the Einstein theory is non-renormalizable, and something that you can do to make the theory renormalizable is by improving the behavior of propagators when energies are large. So this propagator is a higher derivative, typically a higher derivative propagator, and it falls off more rapidly than the normal propagator 1 over p squared. This is sufficient to make the theory renormalizable. It has been known since the 70s in the so-called stellar theory, which we will meet along with the talk. The point of these propagators is that when you decompose their poles into standard poles 1 over p squared, there is necessarily one of them that's multiplied by the wrong sign. Okay, a relative sign, minus sign, is always present. So these violate unitarity. Well, that's not actually true. They violate unitarity if you quantize them as you normally do. So let's talk about this crucial issue, that's unitarity. Unitarity is a statement that the S matrix should be unitary. Another way to phrase the statement is by decomposing S as 1 plus IT, and then the same identity is written in this form, which is called optical theorem. If you insert states of your Fock space, A and B, in and out states, you can forget about this thing for the moment, forget about that. If you insert a completeness relation, you see this is a completeness relation, then this T dagger T can be written this identity can be written in the form here. So the completeness relation here is unity. Well, the point is that in higher derivative theories, you cannot prove such an identity. This identity is what you would like to have, but it's not something that you actually obtain. What you obtain is a pseudo-unitary equation where instead of having the right completeness relation, for some states you have +1 correctly, and for other states you have a minus. And that minus is due to that minus there. Direct consequence of that. So what you obtain is an identity like this, which does not agree with S dagger S equals 0. It's another thing. And you would like to project the wrong states away. The wrong states are called ghosts. That's not possible. It's not possible to project them away. Why? For example, you can neglect the unwanted states from the set of states that are the in and out states here in your processes. You can decide what states you put as in and out, and if you do not want to have ghosts, fine. But the point is that you cannot decide what appears in this sum, because that is a completeness relation. What appears is predicted by the theory. So that's the problem of higher derivative theories, and why you can, in gravity, have a higher derivative theory that is renormalizable, but then it is not unitary because of these minus signs, and you cannot get rid of them. Unless you use a new prescription that we will see. So to get to the new concept, let's analyze in more detail the diagrammatic version of these identities in the usual case, in the case with no ghosts for the moment. And because the optical theorem has a diagrammatic version, you can write the optical theorem diagram by diagram, and then the identity diagram by diagram has this kind of form, this form in these two very simple cases. This is a three-level identity, and this is a one loop. So you see you have an imaginary part on the left-hand side, and you have something non-negative on the right-hand side. This is crucial, something non-negative, if you have unitarity. The minus signs will destroy unitarity, and that's the problem. But for the moment, if that is okay, you should have something non-negative on the right-hand side. And for example, in this case, you have the imaginary part of this diagram that is equal to this cross-section, the integral over the phase space of the final states. Here there is only one final state. Basically, you take this diagram and you cut it. There are cut diagrams, so-called. If you take the same vertex and rotate it, you get a different cross-section, which is the cut of this bubble. The key property I want to emphasize of this theorem is that it is non-linear. It's quadratic identity. And so you see it mixes different orders. 3-level, 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 one loop. That means you cannot easily project away states that you do not want, because they will, even if you project them away, they will be regenerated as cuts inside level diagram, loop diagram, sorry. We will see more in detail in a moment from the analyticity properties of the amplitudes, because now the prescription, the discussion concentrates on the prescription that you normally use and the new one. So let's take a propagator. This is singular on the real axis. You need a prescription. Normally you take the plus I epsilon prescription. Fine. Is that okay? Of course it is, because now if you use that propagator in this identity, for example, you can check that the optical theorem is correct. And that identity reduces to this thing. It's a simple identity for distributions, and the right-hand side is non-negative. What if you change the sign in front of your propagator? Because, as I said, in higher derivative theories, some poles have the wrong sign. You cannot have the unitarity fulfilled precisely because it is a quadratic equation, and if you change the sign on the left-hand side, you change the sign, but you don't change the sign in the right-hand side. So in particular, if you put a minus sign in front of the propagator, you will have a minus sign to the right, minus pi delta on shell, and that is a ghost. That violates the optical theorem. But observe one thing. that if you change the sign in front of the pole, but you also change the sign of the prescription, then it's okay. So this is a problem caused by the prescription, not by the sign in front. This thing would be okay. Now, can you build a quantum field theory where those two propagators coexist? No, that's hard. For some reasons, they create a lot of troubles. And the fakeon, the answer that I will formulate in a moment, is the only way to make them coexist, basically. What is the answer? So start from this propagator, 1 over p squared minus m squared. You have two poles on the right, on the real axis, and normally you circumvent them like that. I want to emphasize that everything I will say holds irrespectively of the sign in front, plus or minus. So let me put a plus or minus because everything will work for both cases. And what you do is multiply and divide by p squared minus m squared. And now ignore the numerator because the numerator will not cause singularities. And this doubles the poles basically. And you can split the poles into pairs by means of a width, like that. So instead of the plus I epsilon prescription, you use this thing. Well, you start from that because the prescription is not over. It's far from over, actually. But you start from this prescription, and now I will have to tell you how to deal with it. Because if you take it literally, that would be the principal value of 1 over p squared minus m squared, which is not what I will be going to do. But just geometrically, if you take these poles and you imagine to split them into pairs, you obtain something like this, which will be very important, you see. You will have an integration path like this. This will be crucial. You don't integrate here. That will be a Minkowski integration. That will be the principal value. You integrate in this funny way where the left pole, the left pair remains above the contour and the right pair remains below. This contour was first proposed by Lee and Vick in Lee-Vick models, which claimed many years ago to make sense of higher derivative theories, and their theories remained surrounded by skepticism. And I have to tell you that my entire investigation had the purpose of disproving definitely the Lee-Vick models. This is where this started. But the idea of this contour integration, which they had, and so I will call this Lee-Vick integration path, is right. It's not complete. They missed another half of the story, but this is definitely right, and their models I could not disprove, but I could only improve, and that led to the notion that of fake particle. Yes, so introduce this infinitesimal width, and then you will, because I choose it to have dimension 1, but it's not like the other epsilon which has dimension 2. But if you want, you can. Now, notice that on shell, this has no, this is 0. So that tells you that it is propagating 0 particles. That's not true, but the point is it has no imaginary part. So again, the story is not so simple. Now we come to a little bit of technical part, let's say 5 minutes, and then we will go to the more important consequences. So let's say we want to compute diagrams with this strange propagator, and we use, so this is a bubble diagram. K will be the loop momentum, P will be the external momentum. So you have the integral of two propagators, one with momentum K, the other P minus K. The two propagators will be these things, rational functions. The story goes on as usual, nothing particular. You integrate on the loop space momentum, R3, but you integrate the energy on the Lee-Vick integration path. And that tells you, when you apply the residue theorem, which poles you get. Do it. After the integration of that, what do you obtain? You obtain the integral on d3k of a certain integrand. As usual, again. What are the analyticity properties of this amplitude as a function of the external momentum p? Well, first of all, that function is certainly analytic anytime this integrand is regular, everywhere regular, which means that if this integral has no singularity for no value of k in the domain, certainly you have analyticity. So you are interested in the singularities of this, and the singularities occur, as usual again, when you have the external energy equal to a sum of frequencies. So forget about that epsilon. Normally you would have external energy P0 equal to the sum of the two frequencies of the particles circulating inside. Because the singularities are associated with a physical process where the external particle here gives two real particles, where the virtual particles inside become real particles. So again, usual case, no imaginary part, no epsilon. The singularities, when you plot them for k varying in the entire domain, are two branch cuts. You might be familiar with that, simply two branch cuts. But when you have epsilon different from 0, and you plot for k varying on the entire domain, you will see that you fill extended region surrounding the branch cuts. And if you make the calculation into these extended regions, inside you will see that Lorentz invariance and analyticity are violated. And this is where Lee and Vick stopped. The problem was known, and there were prescriptions to circumvent it, but they were never able to remove it completely. One comment, it's in some sense obvious that you have to violate Lorentz invariance. Why? Because you see, if you insist on integrating the loop space momentum on real values, when your energy is integrated on complex values, you are breaking Lorentz invariance. So the only hope to recover Lorentz invariance is to deform the domain of integration on the loop space momentum as well. There should be a prescription, a companion prescription of the Lee-Vick prescription for the integral on the energy. And now I describe what it is. So the answer will be that you have to deform this into something obtained by complexifying even the loop space momentum. In the papers that I publish, you can find every detail, but let me just give you a very simple example of the answer in 2 dimensions, 1 plus 1. In 2 dimensions, you have just one component here. Let me call it kx. And so normally you would integrate on the real line. Well, you discover that if you deform the real line into something like that, very, very simple, when you do that, that region shrinks into branch cuts. Those 2 regions shrink. As long as you deform this, and you recalculate the solution of these singularities, but now k doesn't span R3 or R, but this domain, D1, then this shrinks into branch cuts. So you can say, okay, this is good. Well, that's not good at all, actually. This is just the beginning of the journey. The point is, okay, then what do you do with that? What do we do with that? Because check this picture here. Fine, you obtain, as usual, with this deformation, 2 branch cuts. The point is, how do you compute, how do you define your amplitude? Feynman, the prescription by Feynman says from above, here, and from below there. So the prescription plus I epsilon is you compute, you define the prescription above this threshold. the branch point from above. Above the threshold on the real axis, you define from the above, which means from the upper half plane. And the complex conjugate amplitude is from below. This is bad. Why? Because if you do that, you have a discontinuity, you have an imaginary part, and then the optical theorem would tell you that you have an imaginary part, you have a physical process. A physical process where you produce the virtual particles inside, which means a physical process where you produce particles with complex masses. That's what you want to get rid of. So this is just a technical warm-up. Get into this deformation, which eliminates Lorentz invariance and the violation of analyticity, eliminates the violations of Lorentz invariance and analyticity when you take this deformation. But still the point is, how do you define your amplitude above the threshold on the real axis? Because if you define it a la Feynman from above or from below, there is a discontinuity associated with an unphysical process, and you violate unitarity. Here is the solution, which is inspired by the very existence of this extended region. Okay, let me start again from here. As I said, if you compute inside the region, you violate Lorentz invariance and analyticity. Now I tell you to do the following thing. Go inside the region on the real axis. Compute the integral there. You violate Lorentz invariance and analyticity. Then, from inside, when you are inside, you shrink it by means of the deformation of the domain. Okay? So calculate inside, then deform the domain. In the limit, you will see that Lorentz invariance and analyticity are recovered. And this is the definition, the prescription to calculate these amplitudes. And we will see that this branch point corresponds to a threshold for a fake process. So basically, it's like computing not from above the cut, not from below the cut, but sitting inside the cut. And a mathematical theorem that you can prove is that the result of this is the average of the two analytic continuations. It's literally the arithmetic average of the two analytic continuations. So if you start from an analytic function and you take the average of two analytic continuations, you can check that this is a non-analytic operation. And it's unambiguous, but it is a non-analytic operation. Let me tell you what the result is. In the bubble diagram, you will have a certain threshold, the branch point, and below the threshold, your amplitude, the real part, will be some function. Above the threshold, it will be another function. The two are analytic. But if you do this arithmetic average, you can immediately check that the imaginary part is 0, both below and above. Basically, Feynman would give you this. This is what you obtain by reaching the real axis from above. And the fakeon prescription would give you this. 1/2 the logarithm of the square. That's it. That means that you have broken your complex plane into regions. So let me take this branch cut. Now, since I am calculating inside, let me blow it up in a cone by analytic continuation, so I describe it like that. And you have a notion that I call region-wise analyticity. Normally, you have analyticity in Carter field theory. You compute amplitudes in an open set, and then you know by analytic continuation the amplitude everywhere. Here, the recipe is as follows. You compute the amplitude in an open set of the Euclidean region. Then, by analytic continuation and possibly average continuation to cross these thresholds, you unambiguously determine the amplitude everywhere. And however, the function that you find here is not analytically related to the function you find there. And you cannot go backwards. So from the Euclidean region, analytically or with this average, you can determine the amplitude everywhere, but you cannot go backwards. We'll see in a moment that this new type of analyticity has a physical consequence, which is the violation of causality at very small distances. But the point is that with this prescription, which is completely symmetric with respect to above and below, so it's real, you have no imaginary part. And so you can fulfill the optical theorem, have unitarity. You can do it as follows. Now, if you compute the imaginary part of the bubble diagram with this prescription, which I call fakeon prescription for the virtual particles, the imaginary part will be 0. But that will have to be equal to a cross-section for the production of those intermediate states. So it's sufficient, and actually you have to do it, it's sufficient to say that those states do not belong to your physical space, and you are done. So you use this prescription and you project those states away from your physical spectrum, and you get 0 equals 0. What you could not do normally, you cannot throw away states because they are regenerated by loop diagrams. Now you can do because they are not generated by loop diagrams, because you have touched something inside those diagrams to make things work. So what you obtain is that from the pseudo-unitarity equation, which had this wrong completeness relation where you had plus and minus 1, here with the fakeon, you have, instead of plus or minus 1, you have 1 or 0. Because the imaginary part is the standard 1 or 0. And the 0 are those that you project away. And so if you descend from your complete space to the subspace where fakeons are thrown away, you get the optical theorem. And this can be proved to all orders, not just for the bubble diagram, where you can follow everything indeed, and it's very, very simple, but it can be generalized to all diagrams, as you can check in this paper. And now you can build the theory of quantum gravity. Why? Well, the Einstein theory is non-renormalizable, Einstein plus cosmological term, but this theory, this is the simplest renormalizable model, higher derivative model, and you have r squared, and this is Weil squared, basically, with two parameters, alpha and psi. I choose the parameters zeta, alpha, and psi. They are a bit redundant here, but it's useful to have redundant parameters. Anyway, they are all positive. They are all positive. And then if you want, you can include the standard model coupled to gravity. Now, this theory is known as stellar theory if you quantize it a la Feynman, and it is known to have a ghost. Now, what is that? That is a pole with the wrong residue. But the pole with the wrong residue can now be quantized as a fakeon. Actually, you might tell me, even a pole with the right residue you can quantize as a fakeon. We will come to that. Yes, that's true. Even a pole with the right residue you can quantize as a fakeon. Not necessarily. But certainly you have to quantize like that the poles with the negative residue. So there is a way to eliminate the higher derivative, to make the long story short, by means of extra fields so that you can see all the fields. You might be familiar with this. Anyway, you rewrite that action as the Hilbert term. Cosmological constant is 0 from now on because I don't want to be bothered by that. Then you have a scalar, and its kinetic term is fine, positive sign. And then you have a spin 2 massive field, which is a complicated action. but its action is a Pauli fields with the negative, with the wrong sign in front. No minima couplings and vertices, forget about those. So this is the crucial thing. If you take those higher derivative theory, and you eliminate the higher derivatives, you will get something with the wrong sign, as we know, because the propagators of higher derivative theory necessarily at least have one pole with the wrong residue. Then you have to quantize this field chi mu nu as a fake. And this way you have renormalizability and unitarity. But as we said, you can quantize as a fakeon also a field with a positive residue, so phi could be a fakeon or not. And that only the experiment will be able to settle. So in the end, this theory of quantum gravity is described by a triplet. One is the graviton, the fluctuation around flat space, for example. Then you have a scalar field, which could be fake or not. And then you have this spin 2. I put this transparency because before moving to the classical limit, I want to emphasize once again that this is a theory where you can calculate everything as you do with a standard model, differently from every other approach to quantum gravity where you can calculate basically nothing. Here,
Scalar is optional or is it?
no, it's necessary. You cannot do anything because this theory is so constrained, basically, and unique, that to make everything work, you have the option to quantize phi as physical or fake, but you have to have it. And that is one
The mass of the spin 2 fakeons. This is the Pauli mass, so you send to infinity?
No, this is a physical parameter, and it's a ratio of two parameters in the. How large could it be? It could be much, much smaller than the Planck mass without clashing with any data. It could be very, very small. My feeling, but I have no strong argument, is that it could be around 10 to the.
It has physical meaning?
Yes. Has physical meaning, and it is the scale at which you start violating microcausality. So it's, if you want, not a mass of a particle, because there is no particle, but it has a physical meaning. So here you can compute things as you do in standard model, for example, the bubble diagram, which you can find in these two papers with Marco Piver, who did his PhD on this theory, and now is a postdoc in the States. You can resum the bubbles and compute the width of this particle, for example. The width is related to certain things called central charging, homomorphic theories, related to the number of scalars, fermions, and vectors in the matter sector. But the point is, check out the sign. The width of the fake particle is negative. What does it mean? It means that causality is violated. But causality is violated in many other ways. So in the end, you have a theory which, coupled to the standard model, makes this nice table with triplet, and that could be the theory that explains everything we know, with, in addition to what you expected, the graviton, you have a fakeon, at least one fakeon, and a scalar field. Now you can ask me, okay, are you sure that there is no fakeon around here? No, I'm not sure. There is the open possibility is that H is a fake. Still open from the data. I will comment on that at the end. Because again, you can quantize as a fakeon even something which has the right sign of the residue. Okay, maybe I can jump to this comment and tell you about this, and then we will go back. So this idea is indeed a universal idea. So in the standard model, for example, you cannot predict which is the set of massive particles you have. You can always add as many massive particles as you wish, as long as they are heavy enough and nobody ever detected them. But those particles that you add could also be fakeon. So you could, but the interesting question is there a fakeon among the list, in the list of particles we already know of? And how to determine it? So one thing is that a fakeon is not an asymptotic state, it's only virtual, so you cannot see it. So if something exists but you cannot see it, it could be a fakeon. The point is that the Higgs field we didn't see the Z, we didn't see the W because they are short-lived, they don't get into our detectors. We studied processes where you produce a Z, for example, and then you collect the products of decay, and then you plot them, and you check that everything is in agreement with the existence of a Z for some mass, and so on and so forth. So how do we check that Z, for example, or W is not a fakeon, or is a fakeon, without detecting or looking for W or Z directly, which is impossible? Well, because the fakeon prescription changes the imaginary parts of loop diagrams above certain thresholds. So you have to check in this peak the loop corrections above certain thresholds. For example, if you notice here in this diagram, there is this kind of thing here. And you see here W plus W minus. What is this thing? Check that this threshold is twice the mass of the W, 160 GeV. What is this W? This is precisely the imaginary part of this diagram, the cut. The threshold, and above the threshold, the imaginary part of a one-loop diagram is a square root. You might remember from textbooks. This is a square root, you see. Now, fakeon or real will change the coefficient in front of the square root. And you will see something different here. Maybe there, maybe there, maybe there. So if you are sufficiently precise, you can understand whether W is fake or not. Since nothing was noticed, no contradiction with expectations, you can assume that W is not fake. But the point is that H, the analog for H, there is a process with a bubble that involves H, has a threshold that was not reached by LEP. Perhaps it wouldn't have been precise enough. That was, so Lab 2 stopped here, 209 GeV, and that threshold would start here, 216. And so there is a way to determine whether H is fake or not, checking the analog of that and seeing if it is as expected or not. But you have to reach those energies with a sufficient precision. Now, LHC, of course, can reach much higher energies, but it's not equally precise, and so maybe the answer is already buried in their data, I don't know. Some work should have to be done, or in the worst case, in the next generation experiments, we'll certainly be able to answer the question. But it is a question that has a definite answer, so there is a way to prove one way or the other. And so far, I cannot tell you which answer it is, because I have no reason to claim that H is fake and no reason to claim that it is not, because everything else works as it should. The symmetry breaking mechanism, everything else is exactly the same. Just to point out that what I claim is that just a little detail had been overlooked, and now it's interesting to go backwards and start again from the beginning and see what changes in every sector of quantum field theory. Look for ways to detect some physical implications. For example, there is a violation of microcausality, which you have, I have already pointed out here. This is very difficult to detect. This would be very difficult to detect even if the mass were not so large, because I asked phenomenologists, have you ever proved, can you prove to me that the width of the muon is positive? And they told me they cannot. They never thought of making experiments to check that the width of the muon is positive. So I don't know, maybe they can be done, but they didn't so far. But we will see that the violation of microcausality survives the classical limit, because there is something interesting in the classical limit and unexpected that changes a little bit of things. So let me comment before going to the classical limit on the projection in general. Here you have a generating function of physical fields and fake fields, fakeons. But the fakeons are not asymptotic states. What does that mean? Well, basically, when you build your Cartesian function, you just don't put sources for those. You only put sources for the external fields, physical fields. And this way, the chi is integrated, so it's only virtual, but you have to quantize it in the way we have explained. So every diagram where there is a chi inside has to be computed with those techniques. And so what is the classical limit? The classical limit is a set of 3 diagrams with no fakeons as external legs. This is not the starting classical action. We started from a classical action that cannot be the classical limit. So we started from a classical action. It was a higher derivative action. We knew it had something redundant that had to be projected away. Now that we know how to project away, we can take the classical limit. So I call the initial action an interim classical action. You lift quantization, the quantization procedure in some sense, because the virtue of the action I started with is that it is local. After the projection, it won't be local, indeed. But here it is. If you want an example of the idea, take a gauge fixed action. The gauge fixed action is a classical action. It is redundant, it has unwanted degrees of freedom, it is unprojected, but it has one nice thing, it's local. So you work with the unprojected action, you know that it is not the classical action, you keep it till the very end, and you project only at the very end. Only at the very end you project away for the Popov ghosts and the temporal and longitudinal modes. Now, you can think of my interim classical action as something similar, local but unprojected. You have to project it at the end. The difference with the gauge case is that in the gauge case, after the projection, you won't violate causality. Here you will. Why? So basically, the projection works as follows. You take the starting action, you work out the field equations, and the projection is as follows. You take the fakeon, for example, its equation, you solve it with no freedom of choosing initial or boundary conditions, because you have to solve it with the fakeon prescription inherited by the quantum theory. So it's blocked, and you insert the solution into the other 2. And what is the fakeon prescription in the classical limit? Then in that limit it is a principal value. And then you understand why you violate causality, because the principal value is the half sum of the retarded and advanced potential. So there is an advanced potential. I can illustrate this very simple with a non-relativistic model so that it clarifies everything. Take this is a normal theory, Lagrangian mv squared divided by 2 plus an external force. Then I add some higher derivative terms, and the equation becomes this one. Now the kinetic operator on the left-hand side factorizes, and now you take this factor and you invert it, and you send it to the right-hand side, and you invert it with the fakeon prescription. And then you find this equation, which is not f equal ma, but is ma equal to some convolution of f with a very rapidly oscillating function, and this tau is basically 1 divided by the mass of the fakeon. And that is where you violate microcausality, even in the classical limit, because basically this equation tells you that if you want to solve your model, you need to know your external force not just in the past, but also in a little bit of future. How much future? Tau. Because for long intervals in the future, this is so strongly oscillating that it won't matter. But at least for a small amount of time, that is important. How small could it be? If this mass is 10 to the 12 GeV, this tau would be 10 to the minus 36 seconds. 10 to the minus 36 seconds is so small that there is no possibility of ever detecting a contradiction. I would like to remind you that the smallest, the shortest amount of time that has been measured directly is the attosecond, 10 to the minus 18 second, directly. If you go to the width of z, which is an indirect measurement, then you can say 10 to the minus 25, 10 to the minus 26, 24 seconds, but directly it's far, far from this amount of time. Let me see, 47 minutes. So, okay, so maybe I can conclude with some comments on less simple cases, because this is a free theory, so you might not be satisfied with that, since I am aware that problems with causality are involved in cosmology. Why not see if this theory predicts something right after the Big Bang? And okay, that's a long journey, and I'm far from giving you answers, but just to describe how to make this projection in the case of the Friedmann-Robinson-Walker metric, let me illustrate what happens in that case. So this is the metric, Friedmann-Robinson-Walker, and it's conformally invariant. The Weil tensor is 0, so basically the fakeon doesn't contribute. So I really have no reason to study it unless I am assuming that phi is also a fakeon. So I will assume that phi is a fakeon, and basically you are reduced to studying the Starobinsky action. Well, let me tell you how the field equations are written. Here they are. Rho and P are the energy density and pressure. And the remarkable thing that maybe people did not notice before is that they factorize. So these are the unprojected equations. They are projected, the equations of this action. They factorize these operators in the same way as here you see you factorize. But that's free theory, so that's flat space. You factorize everything, always. Here it's non-trivial. You factorize this operator, which is, by the way, the covariant box for a scalar. And here you factorize this other more complicated operator. The point is that you factorize them, and so you can invert them and throw them on the right-hand side by means of the principal value, and that will be the projection. So you define a kind of average by means of a half sum of the retarded and advanced potentials, and you will get these kind of equations where on the right-hand side you have moved these two. So they look pretty much like the standard Friedmann equations. And actually, if you want to put them in a Friedmann form, you can even define a certain, redefine rho and P to have them exactly in that form. Rho tilde, however, and P tilde are related to rho and P by a complicated formula, which is this average, and the average is complicated to work out. I use this just to illustrate some features of this thing, to emphasize two things. One is The classical limit, again, is not the classical theory I started from. It has to be studied anew. Second thing, and now I want to tell you, the classical limit bears so many features of the quantum theory it comes from that I do not even have closed forms for the classical field equations. So remember, the projection comes from the quantum theory. The quantum theory is defined only perturbatively. What happens is that the classical limit, the classical theory, is defined only perturbatively. What does that mean? Apart from some very specific cases, which I summarize here in this case, where you can solve the projection exactly, and you know that in quantum field theory there are always quantities that you can resum to all orders or compute exactly, very few ones, anomalies, renormalization group, the widths, the resummation of the bubbles. Apart from those specific cases, you always run into asymptotic series. Asymptotic series, yes. And here it is the same. So I will give you the example of the exact things. You can find the exact solution with the equation of state of this is energy, radiation, and the vacuum energy density, and the combination of the two. This is exact. But as soon as you start studying a slightly more complicated problem, dust is complicated, you run into asymptotic series. And again, I want to describe this with a simple model, which is again our model we had before, but now instead of an external force, I introduce a self-interaction. Well, what you get when you project that equation is that if you study the projection, which is defined perturbatively, you want to handle it, you will end with an equation that is, by projecting away the unwanted degrees of freedom, so you will reduce your higher derivative equation into a normal derivative equation, but you will have an infinite sum to the right-hand side. And the coefficients will grow so fast, check it, that you can have no hope of making it converge. Otherwise, however, it is an asymptotic series, and so if you plot it, for example, the solution, you will see that if you take just a few orders of the expansion, it will be remarkably precise. Here, for the coupling equal to 110, it will be remarkably precise up to 10 orders. There is this relation, and then it blows up completely. So I'm stressing again, this is in the classical limit, and it is the classical theory which bears the features of the quantum theory comes from, because if you would like to go beyond the perturbative definition of the fakeon and its prescription, you would have to solve quantum gravity non-perturbatively, and this I cannot do. So I think I can stop here. Okay, so let me make a final comment on causality. You might, I have given many talks so far, as you can see, and I noticed that nobody cares about causality, so that's a fair price to pay. There is a reason that I understood, is that causality is so poorly understood that it's hard to elevate it to a physical principle, because in quantum field theory, this is Toft-Veltman diagrammer. You can check what they say about causality, and they point out something very clear and true, that we do not have a notion of causality in quantum field theory. We have definitions like the one of Bogolyubov, or the Lehmann-Simansik-Zimmermann one, fields commuting outside of Lacan. Those two are off-shell. They are not directly related to observable quantities. The reason, the trouble, he says, is that you cannot accurately pinpoint space-time points with relativistic wave packets that correspond to particles on shell. And you can check the identity, the diagrammatic identity they give for causality, and it's an identity for off-shell Green functions. It's hard to elevate to a physical principle something that you don't know much about. So I do not even think that this is a drawback of my theory. I actually think that it is just a prediction, because if you study quantum gravity, you have to expect some new understanding of space-time at small distances, and this is it. You have no causality there. At sufficiently short amounts of time, you have no past, present, and future. That's all. No strings, no loops, no holograms, no infrared fixed points. All these are, in my opinion, fantasy proposals that have no hope to have any success. And what is the strong what are the strong features of my proposal? It's close to the standard model. It's the only open spot that remained in quantum field theory. It's a quantum field theory. It has a perturbative expansion in terms of Feynman diagrams. You can do calculations. It could even be the most predictive theory ever. Just imagine that with two parameters you can go from astronomical distances to and beyond the Planck mass. So it could be the most predictive theory ever. So my bet has always been this. We have no clue and no data to venture into fantasy land. The only hope was that the standard model was just one step, that quantum gravity was just the last mile of the standard model. Precisely as in this famous case, where out of this decuplet, 9 particles were known, and it was a surefire to predict the 10th. So I think that this is the standard model, and this is quantum gravity. Thank you. Sì, sì.
Any question? Do you have a canonical prescription for constructing the fakeon quantization? Using operators?
No.
Like from phase space, canonical?
This is...
Maybe it's not where it was the question, in the sense you have the...
This is one of the many, because everything, what I told you is everything we know. And even, for example, if I want to formulate the prescription in coordinate space, that's a challenge. That's a totally open area to investigate. Everything I said is to build an S matrix in momentum space, and there you know what to do with these things. And then if you want to go beyond that, you have to study it through from the beginning, probably challenging. It's one of the many things I have in the list. No, there isn't already, but that doesn't mean it will. It's not. Yeah, there isn't, because it's challenging. It's to be done. To be done.
I have a question. Concerning the cosmological part of your idea, the scalar field emerging in the Starobinsky model is usually responsible for inflation and give rise to the cosmological perturbation during the inflationary phase. If it is a fakeon, you have consequences on the primordial spectra.
I am working on that. Actually, 2 students are now working on that. And I wish I could tell you already something, but I cannot, because the subject is, to me, very complicated, because I'm not a cosmologist, so I'm moving. And for example, I cannot even exclude, for example, at the moment that phi, the inflaton is a fakeon. I cannot exclude that. I thought I could, but I don't feel confident enough to make claims yet on those areas. But that's precisely what we're going through now, both for the consequences on typical standard problems like the flatness problem, the horizon problem, or more specifically the NS indices, the spectra, and the predictions, and how they are affected.
Okay, there are no other comments. We can thank the